Thank you, Dr. Hishinuma, and thank you, Professor Yamamoto, Koshiba, and Dr. Scheffler for inviting me to the event. It's a great honor to be here, and let's start my presentation. We initiated Tsuruoka Metabolomics Cohort Study in 2012 in Tsuruoka to integrate the metabolomics with the population study. The Tsuruoka is located in the southwest part of the Tohoku district, and then Tokyo is here, and 200 miles north from Tokyo. The participants were 11,002 resident workers in Tsuruoka, recruited for 3 years at the time of the municipal and worksite health checkup program. Age range were between 35 and 74 at baseline, and the participation rate was 89%. We collected the biospecimens, including the plasma, the serum, the urine, and as well as the buffy coat. And we also collected the various lifestyle and health information through the self-administered questionnaire. And for the metabolomics, the validity and the precision of the measurement is prone to the sampling, the storage, and the measuring conditions. So we optimize the sampling, the measurement, and the QC procedures for the large-scale the metabolic measurements. In this cohort, we employ the CE, the capillary electrophoresis mass spectrometer for the polar, the hydrophilic metabolites over 100, and then LC mass MS for the more than 200 neutral hydrophobic metabolites to cover the wide range of the metabolites. At the very beginning of the study, we started with the quality control issues of the metabolic measurement when the metabolomics was applied to the large-scale epidemiology. So reliability of the measurement values are critically important to avoid any biases or the misclassification. All these factors are quite important to get the reliable results. And then the first one, for the subject conditioned sampling, we obtained overnight 12-hour fasting samples for blood and urine. We also examined the sampling and storage conditions, like the choice of the serum plasma, or what kind of the anticoagulant to be used, and then the storage, the temperature, and also looking at the stability of the measurement standards. I will show some results. You see the good correlation between the serum and the plasma metabolites concentration by CE, and then, but then you also can see some exception here and here. So we explored why this exception, and then we compare the time course of the metabolite concentration from the serum and plasma over 6 hours before the centrifugation, and show you the PCA result of the metabolite profile over the time course. And then for the plasma, over time course, the results stayed almost the same place, but then in serum profiles were largely shifted over 6 hours. So we further explore the reason of this shift, and then changes in the acidic amino acids such as the aspartate and the glutamate concentration. Their concentration increased over the time like this. On the other hand, the sulfur-containing metabolites such as cysteine in serum decreased over the time. Therefore, we decided the conditions, and we chose the plasma for the blood specimens, and we also introduced the routine measurement of the shared sample, the quality control. All sample preparation has been done within 5 hours since blood drawing. And we also implemented the measurement of the QC standard, quality control standard, every 10 measurements using the same pooled standard. So reliability issues for the both plasma and urine metabolomics with the CE mass was already published in these, and I'll show a brief result. This slide shows the reproducibility of the quality control samples in the CEMS. One QC sample was injected every 10 subject samples, and for the plasma, overall median QCCB, coefficient of variance for the QC samples, was 15.5% overall, and slightly higher for the anions, 18.9%, and 7.9% for the cations. And then almost 70% of the metabolites, its QCCB was less than 20%. And then the result was similar in relation with urine as well. We also evaluated the inter and intra-batch QCCB by the mixed model. And then the pink bar represents the inter-batch CB, and the blue represents the intra-batch CB. And the left panel shows the result of the QC samples. And then despite a long period of the measurements for the 52 months, inter and intra-batch QCCB was also controlled well. Of course, for the participant samples, the results are varied like this due to the interpersonal difference in the metabolism. This table shows the result of the comparison with the other famous platforms with mass spectrometry. And this is our result, and overall the QCCB was 15.5%, and we picked the common metabolites and compare the QCCB with the metabolome platform. It was 10% versus 9.6. It's very comparable. And for the biocrates platform, 6.0 versus 6.9, and for the Broad Institute platform, 10.7 versus 16. So it's very good in agreement. As you know, we Japanese have a significant lower risk of ischemic heart disease, like this, Japan here, and the US, UK, Germany here. And on the other hand, the higher risk of having cerebral vascular disease in Japan. So with regard to the metabolomics epidemiology, it is of value to conduct a cross-ethnic, cross-cultural comparison to examine if metabolites disease relationship is the same across the multi-ethnic, multicultural cohorts or not. So some groups of the metabolites may be the common. That could be the common mechanistic pathway of disease development. But some might be different, which could explain country-specific features of disease risk. As a whole, we are working on the integrated approach for the prevention of the non-communicable disease, mainly focusing on the cardiovascular and metabolic diseases. So we found the mediating metabolites of cardiometabolic with relation to the cardiometabolic lifestyles like physical inactivity, obesity, diet, alcohol drinking, and smoking. We also the research for the relationship with the cardiometabolic risks like dyslipidemia, the metabolic syndrome, and NAFLD. And then you see the BCAAs were clearly associated with the physical inactivity, obesity, metabolic dyslipidemia, metabolic syndrome, and the menopause. So we performed a collaborative analysis with the neuroimaging study part of the BLSA, the Baltimore Longitudinal Study of Aging, to compare the association between the blood metabolites and the metabolic syndrome across the two different populations from the US and from Japan. In this study, we matched on Asian 6 and 104 participants from the Tsuruoka TMCS and matched 146 participants from the BLSA US included in this study. And for this study, The serum metabolites were quantified with biocrates platforms with overnight fasting samples. For the participant demographics, BLA participants were a little bit older and more males despite mapping condition. But the prevalence of the metabolic syndrome were very comparable, and also the waist circumference and then the fasting glucose level are very comparable. For the BLSA participant, having the significantly higher the percentage of the elevated triglyceride level and higher percentage with the reduced high density lipoprotein HDL cholesterol, and a lower percentage of the elevated blood pressure, and higher prevalence among the TMCS Japanese participants. And with regard to drug use, the BLSA participant had a higher use of the lipid-lowering therapies and a lower use of the anti-hypertensive drugs. In terms of the diabetes medications, both are very comparable. Here we present the metabolites that were associated with METs and their component risk factors, the METs and then the waist circumference, triglyceride, HDL cholesterol, fasting glucose, and blood pressure. In the left, you see the common metabolites, both in the BLSA and the TMCS, and then hexose, and then the phosphatidylcholine acyl alkyl, PCAA, and sphingomyelins were associated with the METs in both cohorts. And they are also associated with the elevated level of the glucose, the triglyceride, and the reduced HDL cholesterol. In the middle and the right panels, you can see the associated metabolites unique to the BLSA in the middle and then TMCS in the right. In BLSA, you see a lot of metabolites across all classes are uniquely associated with all outcome, the METs and other risk factors. With regard to the METs, the alpha amino adipate as biogenic amines, and then acylcarnitines, and lysophosphatidylcholine, PCAA, sphingomyelin, and ceramides were associated with the METs. On the other hand, in TMCS, relatively few metabolites associated with the METs and other risk factors. In terms of the METs, the valine as the amino acid and SDMA as the biogenic amine, and then free fatty acid. Only 3 types of the metabolites are associated with the METs. So in the second study, we more focus on the polar metabolites such as amino acid using the same framework. So now we use the CEMS platform at Keio IAB, and we again matched on age and sex from the both cohorts. And then this time we obtained the 252 participants from the BLSA and matched 644 participants from TMCS. So the size of the study enlarged. Here, I'll show you the comparison of demographic characteristics. And the results are almost the same as the study number 1. So BLSA participants were on average a little bit older and more likely male compared to TMCS. And again, this time again, the prevalence of the METs was similar between groups. And BLSA participants has a greater prevalence of the elevated triglyceride, and then higher prevalence of the reduced HDL cholesterol. And again, the TMCS participants were more prevalent for the elevated blood pressure. And this figure shows the results of the 25 most significant metabolites associated with METs. And from TMCS left side, and from the BLSA in the right side. In contrast to the study number 1, this time 18 from top 25 metabolites are common to both cohorts. and 7, while 7 are unique within each cohort. You can see that these kind of red bolded font indicates a common metabolites like glutamate, the proline, methylene oxypentanate, isoleucine, and leucine like that. Result remained consistent in 3 different sensitivity analyses, including the further adjustment of the smoking, the physical activity, and diet. And also, we did the sensitivity analysis with the sex stratification or excluding imputed values. And then we additionally categorized them into the metabolic pathway for 18 common metabolites based on the HMDB pathway database and the literature search. And we identified 7 the primary pathways. In table 2, these are the 18 metabolites that are common to the both cohort. And then the primary pathways were the glucogenesis here, the glutathione production, the amino acid metabolism, and here you can see the BCAA metabolism here. So the overall result and implication from our 2 studies. So despite the similarities in the prevalence of meds in both cohorts, as well as the similarities in diet, we found differences for over 80% of metabolites included in the analysis between the cohort in study number 1. And in study 1, the BCAAs and sphingomyelins and hexose are identified as the common metabolites. But then on the other hand, in the study number 2, 18 common and overlapping metabolites were associated with the meds, including particularly the amino acid metabolic pathways represented in this result potentially implicate the branched chain amino acid metabolism and the glutathione synthesis in the pathogenesis of meds from the study number 2. So there may be a few explanations for this discrepancy between our two studies. One is the sample size. In the study 2, that the larger sample size, nearly 6 times larger for the TMCS and twice as large for the BLSA, which increased the statistical power to detect the difference. And also the metabolics platform was different. So quantifying the metabolites by CMS in the study number 2 to more focusing on the polar metabolites. For BCAA, it's proposed that cyclic BCA concentration reflects the various dietary intake of BCA-rich foods like this. And then circulating BCAA causes type 2 diabetes and the cardiovascular diseases with the impaired the BCA metabolism. However, the association between the dietary intake and then the blood BCA concentration is not the same across populations. In some countries, it is well correlated with the dietary consumption from the meat, fish, and dairy products with the blood BCA levels. But in our cohort, we examined the relationship between the food intake and the plasma concentration of the metabolites. And then you see the meat, fish food, egg, so the dairy products intake like this low. And I will show the result of the correlation matrix. And then the varying the isoleucine and the leucine here, and blue represent the almost no correlation between these 2 factors. So, and then other studies from different countries showed the similar result. So further analysis with cross-cultural comparison could explain such discrepancy that could be a key contributing factor that explains large differences in the ischemic heart disease risk. The similar example is the TMAO, 3-methylamine N oxide. This is well known as the good flora-dependent metabolite converted from the phosphatidylcholine from the dairy sources that is converted via the good flora and the liver via the choline, the TMA to the TMAO. which is the causal to the promote the atherosclerosis. And then, however, in our study, the plasma TMA concentration was not correlated with the meat, but well correlated with the efficient seafood intake. This shows another example of the difference in diet metabolite relationship across countries. So this is the final slides. And the role of the multicultural, multi-ethnic comparison in metabolomics epidemiology. And the circulating metabolites reflect the interactions among the genome, the good microbiota, and by wide variety of the environments. Therefore, to find the key metabolites that could mediate the pathophysiological pathways of disease development and to understand region by region the ethnic differences in disease risk, international collaborating study of the multicultural, multi-ethnic setting may provide clues about the role of the metabolites. These are our research group and collaborators. Thanks for all, and thanks for your attention.